Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and today we have yet another video. And no, it's not about R. Today we're revisiting Brian Mullins, and we're looking at a video that I had skipped a little bit earlier, and that is the flight over the North Pole. So let's have a look and see how Brian misunderstands Coriolis and see if we can help him out a little bit. So cue up the music, and let's go. Now, I obviously have a little problem with my eye right now, and the studio lights irritate it quite a bit. So I'm going to kind of pop out of this video a little bit more than normal. I'm still here and I'm still going to make my commentary, but I'm going to turn this over to our favorite flat earth engineer, Brian Mullen. So let's go.
Hi, I'm Brian Mullen, and this is Balls Out Physics, episode 1.2, Flying Over the North Pole. I gotta thank Deep Inside the Rabbit Hole for pointing this out, because it really helped me develop a south-north-north-south flight problem, where I think the issue that I was trying to explain in episode 1.0 is really shown. And so, what I have here is a view of the Earth looking down on the North Pole, kind of like I was talking about in episode 1.1, looking down on the North Pole like this. What I have is Quito, Ecuador here, and Singapore over here. And so if you look at this on the globe right here, Quito is right here in Ecuador. We're going to say it's right at the equator. It's a little south. Okay. We're going to take a flight from Quito over the North Pole to Singapore over here by my thumb. Okay. Now, Singapore is at 104 degrees east of the prime meridian, and Quito is about 78 degrees west. And so that's 182 degrees between them. But I'm showing a straight line here. We're just going to assume that they're 180 degrees away from each other. And the runway at Quito actually faces almost due north. So we can say that the pilot's going to start off and fly directly at the North Pole. Okay?
Well, right off the bat, we have a couple of misunderstandings on the part of Mr. Mullins. First of all, the direction that the runway is pointing is immaterial. When planes take off, they can literally circle the runway an indefinite number of times and then take off in whatever direction they want to go. So the direction of the runway is immaterial to this problem. Second of all, the shortest distance between Quito, which is right here, and Singapore, which is on the other side of the Earth, over there, does not go over the North Pole. That is the Great Circle course between those two cities. Now, just to make things a little easier on Brian, I went ahead and I created a course from Quito to the North Pole. This is a due north course following a degree of longitude. Now, I do want to point out something here. This is a line on the sphere. As you see, it's very clearly curved. That is another line on the sphere. These are lines that connect points by the shortest available route. Now, what's the radius? Who cares? It doesn't matter. The only time that knowing the radius would matter is if you wanted to know the number of miles between those 2 points. If you knew the number of miles between those 2 points because you flight planned it, you could actually calculate the radius from that. But there's another thing that I want to point out. This, by definition, is a line on the surface of a sphere or a spherical geode in non-Euclidean geometry. That is also a line on the surface of a spherical geode in non-Euclidean geometry. Nathan, what is this right here called? You have a line that way, and you have a line that way. You have a vertex right there. What do they call this gap right here, Nathan? Is it called an angle? Is that on a curved surface, Nathan? Just go ahead and have a quick look and think about that for a few minutes. So let's let Brian talk about this trip from South America to the North Pole. Now, on the other side of the Earth heading over towards Singapore, you'd run into the same issue that he's going to bring up, except it's in reverse.
And so when a plane is sitting on the runway, it's moving with the Earth, right? If in the heliocentric model, if the Earth is rotating about its axis, we're all moving. I'm moving, you're moving, we're all moving at different speeds based on how far we are from the equator. Well, that's the way I figure it out, at least. And so at the equator, I'm going to say here that the circumference is 25,000 miles. You could say it's a little bit less, but we're just going to keep it simple and say 25,000 miles. And we're going to say that the Earth makes one rotation in 24 hours. Now, you could argue that in a heliocentric model, the Earth makes one complete rotation in a sidereal day, which is 23 hours and 96 minutes, but that's a topic for another time, and it's only 4 minutes difference. And we're also going to say, to keep things simple, that the flight from Quito to Singapore takes 24 hours. And we're also going to say that that distance is 1/2 of the circumference of the sphere. We're assuming a perfect sphere here. And so that's 12,500 miles. And if it takes 24 hours, that gives you an average flight speed of 521 miles per hour.
All right, so far so good. I'm pretty much in agreement with Brian on this matter. Now we're going to do things slightly differently because he's got an improper course there. We're going to use my course, which is from Quito to the North Pole. Now, if you make the other half of the trip, you're just repeating that same trip, only in reverse. So the principle will easily be handled, just going from South America up to the North Pole. But let's go ahead and continue.
So now, when the plane is sitting on the runway in Quito, facing north, here on Quito, the Earth is rotating, right? And so, if the Earth makes one rotation in 24 hours, 25,000 miles circumference divided by 24 hours gives you speed and instantaneous velocity on the Earth of 1,042 at the equator. At the equator gives you an instantaneous velocity of 1,042 miles per hour. Now you notice for the plane, I wrote speed instead of velocity because in physics, speed is just a rate, whereas velocity is a rate and a direction, or having a vector. And I'll get back to that in a minute why I wrote speed there. So the plane is sitting in Quito, use a marker here to represent the plane, facing due north towards the North Pole, and it takes off and leaves the runway. And as the plane begins to fly towards the North Pole, well, the speed of the Earth below the plane would change, right? Because since velocity is distance divided by time, or speed is distance divided by time, whatever you want to look at it, the circumference of the Earth around the axis of rotation decreases as you fly north, right? Because the Earth is curved. And so I just did this by drawing in CAD. When the plane gets to New York City, or at the same latitude as New York City, around there, the speed of the Earth has dropped to 800 miles per hour. But the plane should still be moving at VE, the velocity at the equator, with 1,042 miles per hour, right? Because on the runway, it was moving 1,042 miles per hour. What slowed it down?
Okay, so right here we're going to see where Brian's error is. Now, Brian very correctly points out the fact that the rotational speed of the Earth will slow down as you move from the equator towards the North Pole. However, by how much? He's saying that the plane is moving 521 miles per hour. Now, he's using statute rather than nautical miles here, so we're just going to make note of that so that we're consistent. Now, the way we know that is he's talking about the circumference of the Earth being 25,000 miles, and that would be statute miles, and the velocity of the Earth, the linear velocity at the equator, being about 1,042 miles per hour. That, again, is statute miles per hour. Okay, so let's go ahead and just crunch the numbers on this. In 1 hour, you will be 521 miles north of the equator, and that represents 7.55 degrees at 69 statute miles per degree. The rotational speed, 7.55 degrees north of zero, will be 1,032 miles per hour, which is 10 miles per hour less than the rotational speed at the equator. So let's bring out our old friend, the E6B. Now this is the E6B flight computer. Many of you remember this side of it. We can actually use this to calculate our fuel burns and our distance travel. Say if we're doing 150 miles per hour, in 2 hours, as you can see, we'll be at 300 miles down here at just around 6 o'clock. However, on the other side of this, we have our wind triangles. Specifically, we have our high-speed wind triangles. Now, at the end of 1 hour, we're going to be approximately 10 miles to the east of our destination. That's exactly the same as dealing with a crosswind from the west of 10 miles per hour. So, let's go to the E6B. Now, we're just going to put the E6B on 400 miles per hour right here in the center, that blue dot. Because what we need to do is we need to first put in our wind correction. Now, the dot's on 400 miles per hour. And then if we come up 1 point here, that would bring us to about 412 miles an hour. That's close enough for right now. That accounts for the wind coming out of the west. Now what we can do is come back to our true course, which is north, and we're going to bring that blue dot that we just drew up to 521 miles per hour. Notice that that is to the left of our course. How much to the left? If you look carefully down here at the 500 line, if you look immediately to the left of it, you'll see 5 degrees, and a little further out, you'll see 10. So what this represents is a course correction to the left of approximately 1 degree. And as you can tell, that's such a slight course correction. In the center line, we're still going at approximately 521 miles per hour. In other words, in order to fully compensate for Coriolis, we have to make a course correction to the left of 1 degree from due north. So instead of doing 360 degrees true, we're doing 359 degrees true. That course correction is so slight that even though we have to bleed off a little bit of our northbound speed in order to go a little bit west, it's not enough to significantly change our time over the ground. But do we really have to do this? Is any pilot worth his salt going to wait until he is 10 miles to the east of his course before making a correction? No. You ask Wolfie and any other commercial pilot, they'll tell you that their goal is to maintain their course over the ground between the tips of their wings. That means constant corrections, kind of nudging a little bit to the west to stay over that ground track. So the bottom line is, Brian may make a big deal about this because he never really looked into it. He doesn't know how to do navigation. He certainly doesn't know how to fly an aircraft. And he's never done any calculations like this on a flight computer. But as we can see, it's a 1 degree course correction. That's it. That's nothing. Now, at that same altitude, you can be dealing with 140 mile an hour crosswinds. That's a little more challenging to correct for. So the Coriolis force is a 1 degree correction. And now at the end of this hour, you're directly over that course on the ground. You now go another hour north. And at most, you'll have to make another 1 degree correction. But again, that's not how aircraft are flown. Aircraft are flown to maintain their ground track. That means constant corrections. And the Coriolis correction is so slight, even at 521 miles per hour, the pilots won't even consciously realize they're doing it. The course will they'll just maintain the course, and as they imperceptibly nudge to the west to stay over their ground track, they'll correct for Coriolis the entire trip from Quinto to Malaysia. Now, while many other debunkers have talked about this in the past and pointed out the errors in Brian's reasoning, I wanted to actually show you on a real flight computer how that works and just confirm to you that the course correction isn't anything to worry about. So this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by and taking the time to watch my video today. Maybe next time we'll have a look at Nathan Oakley and learn about R. Take care, guys.
Science Guy.